Douglas Brenner Shocks here in Southern California. I'm authorized Ohlins sales and service for both automotive and motorcycle. I think I'm the only one in the country authorized to do that, and I'm exclusively Ohlins. I don't work on anything else. I'm a shock tech, not a guru. I've done this for over 30 years, and also I know it's hard to believe because I am so young and handsome. I've been racing for over 50 years and doing shocks and putting them in my car and seeing in competitive on-track situations what I've done. I'm not sitting on the internet or just on YouTube. I call them on the internet jabberwankers, telling you what to do when they have no real experience with actual racing or with real competitive drivers. So be careful. I also know I'm not going to be an internet sensation, so I make my money selling and servicing Ohlins products. So give me a call if you need service or sales. You might as well buy it from somebody who actually knows inside and out the product and not a internet reseller. I'm as close as UPS, FedEx, etc. If you need service or bring them over. I'm in Southern California. I'm available 7 days a week to serve your needs. So give me a call if you need something, and I can compete with any price on Ohlins products. Any legitimate price you have, I can do the same or better, and you might as well buy it from somebody who knows the product. So let's see what we have this week. Okay, this video is going to be on pistons and valves. Pistons being like this, that in a shock fork or whatever, that moves through the oil, and a valve, the oil moves through it, which is most of the Ttx technology. Most of the Ttx shocks, struts, etc. Have valves, and we'll go through that later. I've spared no expense to make this display here. There are guys on the internet who made complete shocks that they put on the dyno, and you can watch cabinet. It's fantastic. But this is what I got, and I think it'll help kind of start with the basics of damping in shock as we know it today. This method, I think it's Didion, or it's a French person who figured this all out. And most every shock and struts today uses this same basic technology. So there's ports in this piston, and the valve there's ports too, and usually there's shims over it, and I'll explain why that is, and my next video will be on shims and shimming and what's going on. But basically you're restricting the flow through there to get some resistance to motion, and depending on the size of the ports and all that, the resistance changes. So couple things here. All right, let me get it up to where my little line, hopefully. I think I can see it. So as this thing moves down, it's the thing, as the piston moves down, fluid's trying to flow up through here, and it's being restricted. But you also see, because the shaft is going in, that the level of the fluid raises. And this happens on most shocks, not Ttx 40s, Ttx 46 through shaft shocks, but I'll explain that later. So you can see it's displacing fluid, right? And then as you come up, of course, the flow goes the other way. And one thing you have to take into account is as the fluid's flowing up this way, the shaft's also going in. So the flow is different than in Rebound, where the shaft's going out. So there are, and I'll try to explain it better later on in this video, that's why if you look at most pistons, the Rebound side and the compression side, the ports are different sizes. Now you might ask, why do we need shims? Why can't we just have holes in the piston, a few holes? Well, what happens is as the velocity increases in any size of an orifice, the force it takes at the end of the shaft, or the force it takes to put fluid through there goes up to the square of the velocity. So what happens is either you wouldn't have any damping, or at some point it would just saturate. It would just, the dyno curve would look like this, and it would just hydraulic. There's a point at which it just can't pass any more fluid and it would stop. So the shims are a way to design your dyno curve, and you need it. Now, that being said, oops, this is from a BMW R9T fork, and I think it's Showa. I made a mistake. I'm calling forks in some of my other videos Showas, and I don't think they are. They're some other Japanese brand. But basically, there's no shims in this. This is the seal if we were going to put this in and we had the right size. And there's just holes. That's it. No shims. So this really, either there's no damping or too much damping. There's nothing done here to really design the damping curve. I don't know how they get away with it, but I guess they do. So let's get on to the next part. Here we have a bunch of Ohlins pistons. Some of them are experimental. They were never used in production. They're always looking for better ways to do things, unlike some of the other manufacturers who have had the same pistons for 20 years, 15 years, or they reintroduced a piston that didn't work before. Another thing you'll notice is they're all either steel or, I think this one might be brass. This one is brass. This is brass, but this is a valve, so it's a little different. But Ohlins is really, really good about matching things so that through any heat range, things are pretty linear. And evidently aluminum doesn't do it. There's another manufacturer, they're all aluminum. All their pistons are aluminum. And I used to get TT44s, which were IndyCar shocks in the 90s. Fantastic. Still a fantastic shock. But I get them from IndyCar teams, and I took one set apart, and they'd gone to the trouble of CNCing some aluminum pistons. They mimicked the steel, but they decided aluminum was better. And you know, it's easier to make an aluminum piston. Some of these are sintered steel. But anyway, if Ohlins thought aluminum was the way to go, there'd be aluminum. It's like, it always interests me that people think they know better than Ohlins, because I don't think they do. I think Ohlins knows what they're doing. Okay, another factor on Ohlins pistons is the piston ring. And the piston ring does two jobs in most shocks and forks, etc. But not on TTX 40s or TTX 46 because there's through shaft, so it's another deal. But basically, it not only has to seal on the side of the shock body, it also is the bushing that holds one of the two bushings, one being in the seal head, and the other is the piston ring that keeps the shaft from misaligning and keeps it straight. And Ohlins has chosen to do, I don't know, it's like a inside-out DU bushing. I don't know what you'd want to call it, but it's steel with some sort of a coating, maybe a Teflon or some special coating on it. And it also has a brake in it. And the brake is obviously so you can get it on, but there's another factor in that it gives a little bit of bleed. And this is a piston ring from another manufacturer. It's Teflon. It probably works all right, but I don't think it's as good. So one of the shock gurus decided that he decided that this separation was no good. Like the piston ring needed to be one piece so that it would really seal and whatever. So he made these one-piece ones that I guess they stretched a little to pop on the piston. He had a special tool and everything, and the sales pitch was, oh, you know, it's one piece, it's much better, because of course Ohlins and everybody else is stupid. So I asked my mentor, the guy who taught me all this, Bruce Burness, the wonderful Bruce Burness. I said, what about this one-piece ring? He said, we tried that. What happened was when you got some velocity going, because there was no bleed, the ring would expand, the pressure would get in back of it and expand and cause a lot of stiction. So probably any of these fancy pistons you see on the, you know, on these the companies that make all kinds of accoutrements for shocks and stuff, Ohlins has probably done it. And if they're not doing it now, there's a reason. So anyway, that's the deal. On the TTX, one of the advantages of the TTX 40 of the through shaft technology is the piston ring only does one job, which is sealing the pump, you know, when it pumps back and forth. So it isn't a solid ring like this. It's made for the job it's doing. It doesn't have to do two jobs. So that's one of the many advantages, which I'll go through someday on the Ttx 40. I have them on my race car, so I can pull them off and take them apart and show you. But so anyway, that's the skinny on piston rings. I think we'll start out with this baby here. It's original, pretty original, from the 80s, I think, Ohlins shock, and we'll go on from there. So this is an original piston from way back in the day. I have an original, I think it's pretty original, Ohlins workshop manual. That has this particular piston and this early Ohlins shock in it. My favorite part is the caution. It says, if you get stung by the needle when the gas pressure is on, you must immediately consult a doctor. So don't get stung by your needle. So unlike, let's say, this piston here that's raised, the surface that the shim sits on is raised, this one is flat and inset. So there's no way you can put a port in the side. These are the ports. Here's these are the ports for the compression. This is the compression. I think they call it the rebound side, but this is where the compression shims live, and this is where the rebound shims live. So the ports go straight through, and you'll see on some later, all the later ones, it's at an angle. So they had to use, they have this little shim. It's a triangular shim that, oops, I'm on the wrong side. And that's how they, since they didn't have any bleed around the piston, this is very early. And you know, there's the thing where, well, my shock's 4-way adjustable, 3-way adjustable, 20-way adjustable. All shocks are adjustable. And when they say it's 2- or 3-way adjustable, they just mean from outside. And it sometimes isn't the best adjustment. It's a good thing to have to kind of see where you're at, but you really should, once you find someplace you like, you should valve again for it. So there were pistons you could get with different bleeds. Here's one with a smaller bleed, so the low speed damping. And you see it was cut out, so these ports, this is a port where the oil goes to the other side, could flow. And the same here, you just get, they had them solid ones. This one wasn't made for the rebound side because the holes don't line up with the ports. So that was their low speed, and then you put a shim stack above this. And also what it had was, here's your compression side, and then they had, you got to have a real solid washer to kind of clamp down all the shims and to denote where the clamping shim is. So I don't know if you can notice, but this is at an angle. So the way they adjusted the high-speed damping is they had different angles of these shims. So when the shim came up, it would hit, it would be stopped by this this big thick washer, and depending on the angle you could adjust your high speed. So anyway, that's an original one. Pretty neat. I don't have the band. I don't know what the band, probably was Teflon. I'm not sure. But anyway, so there's kind of an original. Okay, now we've got kind of a, they're fairly early, but it's a 36 millimeter piston. And here we can see, here's the rebound, where the rebound shims live. See the smaller ports? And look at the size of those ports on the compression side. This, you know, you design a piston depending on what, probably in the day, they wanted not much compression and lots of rebound. So these are kind of designed that way. The ports and compression are huge, which means that as soon as the shim's open, it's dumping a lot of oil. So you're not getting much force, and yet the rebound is very small ports. So I was doing, you know, every once in a while I make a mistake and I try to help somebody that doesn't understand what's going on. So they have these little mini bikes that they race. It's pretty big here in Southern California. They go on go-kart tracks. And they even have like 24-hour races. Pretty neat. Anyway, this guy complained because they're really made for kids and things. So I worked on doing some damping, and the damping was horrible, in my opinion. Again, I wanted more compression and less rebound, and I couldn't get it. So first I machined out a little slot, the thickness probably 0.30 of a millimeter, and to make these ports smaller to tempt, and then, you know, you put your shims over that. This is level with where the shim lives. And I tried that, but here's a little tip. What I finally did was I just turned the piston upside down. I made this the compression, this the rebound side, and it worked pretty well. Now, why is there a variance in the size for rebound and compression, other than maybe they want to skew the damping a little? Well, in my first little thing I did with the clear tube, the velocities are different depending on whether the shaft is going in or coming out. You know, and the shaft goes in and compression out and rebound. So really in compression, you need a little bigger port. And usually, if you're not familiar with a piston and you want to put it on and don't know, usually the side with the compression shims have the bigger ports, and it has to do with that shaft going in or coming out. When it's going in, it's harder to push that. Some of the space that the oil that's going through here in compression wants to take up is already being taken up by the shaft, and so it's different. Here's an example of the difference in this dyno sheet. This is a dyno sheet from the Ttx 36 ILX that I did, and this is the stock valving, and the bleeds are the same. It's -10, and it comes with exactly the same damping, or well, the same shim stack, compression and rebound. It's the same, and you can see the difference. The compression, if you go out to like 5 inches, it's 140 pounds of force, where the rebound is 100 pounds, and that's with the identical, everything's identical. So that shows you the difference depending on whether that shaft is going in or coming out. In other words, whether it's in compression or rebound. In the Ttx 40, Ttx 46 strut, you don't have that problem. If that was a dyno sheet for a Ttx 40 with identical valving on each side, the forces would be identical, because there's no shaft displacing oil. All right, so what next? Okay, in my ILX valving video, I talked about why I rough up the surface of a piston always. And I can kind of explain it here. Here's two pistons. This is an earlier model and a later model. And you notice that this has a lot of surface area and it's shiny and smooth. And what tended to happen was from time to time, if you'd see the dyno sheet and there'd be a little blister on it in the compression side coming up. And what it was the shim was sticking for a little bit until I guess it got enough force to unstick it, and then it would open up and it would cause this little lump. And as it turns out, when you have two really smooth surfaces, things tend to stick. There could be different reasons. It could be just the surface tension of the oil that's underneath the that's underneath the shim, or what machinists have when they have gauge blocks and they'll stick together. It's called ringability, where there's two really smooth surfaces. They stick. It's hard to get them apart. And there's a thing called van der Waals forces. And basically, when things are really smooth and really close together, they swap electrons or something and kind of have a real kind of a weak force holding them together. So I don't know exactly what it is. Could be any one of these or all of these. But the way Ohlins mitigated it, all the later, this is pretty late. This might be from a TT44 or something. But you notice the surfaces that the shim sticks to, or that the shim seals, is very small, and they've machined out areas, put little stops here to make sure that there's the least amount of area actually contacting the shim. And I rough them up anyway, just because I'm used to it. And also, if if you're making hundreds of pistons, you can't rough all of them up. They, when they're machined, they're smooth. Also on the older pistons, if you have older Ohlins, this semicircle here, this circle around, means that's the rebound side when it's not really clear. Usually it's clear, which is rebound, because the ports are way smaller. Okay, so this is a digressive piston. I don't use them. I don't like digressive valving. But the idea with a digressive means basically there's a lot of force initially, and then the force levels off as the speed, as the velocity of the shaft increases. There's all kinds of reasons for this, or supposed reasons for this, that I'll go into in another video. But anyway, you can always kind of identify a digressive piston because there's a ring around it. Unlike something like this, where the shim seals the ports, on this, the shim is sealed by this ring. And the reason is this center part is lower than this. So when you have a shim, depending, and there are ones where you can change the preload, but if you push on the middle of this, it pushes in, it preloads the shim. So what that means is it takes a little more force to get this to open, but once it opens, it dumps fluid out. And that was my dumping fluid sound. And then the damping digresses, it gets on linear. So anyway, that's that. And here's a 2-port. It's a 36 millimeter 2-port that was in production. Looks like it's symmetrical. Looks like the ports are pretty much the same size, and they're not giving any indication one's rebound and one's compression. And this was a production piston, but they don't make it anymore, and I really liked it. It did what I liked to do. So anyway, there's another 2-port piston. For some reason, they just don't use them anymore. So here's a really interesting piston. I think it's from NASCAR. It's a high frequency piston. They use them on TTX 40s and TTX 36s. They don't use shims on the pistons on the TTX technology, unless it's a blow-off piston. They make a blow-off piston, but they have all the other parts of it in the piston that moves the oil around. And I guess when you have these hold-down shocks, NASCAR had a ride height restriction, and on the super speedways, aero was really important. They wanted to get the car lowered, so they used the shocks instead of for mechanical grip. They used them to pump down the suspension by having no compression damping or virtually no compression damping and tons of rebound damping. I put one of these on my dyno once, one of these NASCAR super speedway shocks, and it stopped my dyno. So what happens is the shock can come up, or the suspension can come up, but it can't go down because there's so much force. Well, anyway, to get a little damping, especially when they're going that fast, they came up, I think, with this high frequency piston. And you got 21 little ports on either side. It's a rebound side. And they're 1.14 millimeters in diameter. I did the math, and here's the math. And if you're a math guy, let me know if I did it right, but I think I did. So these, if you add up the bleed, in other words, how big, if it was one hole, the bleed would be 5.22 millimeters, which is quite a bit. So what happens is, even though that the piston was way down inside, it was lowered, it could still kind of flutter. Because what happens is you have this O-ring, it's a 3 millimeter gap with a 2 millimeter O-ring, and the O-ring, depending on which side it's on, seals these little holes. So what could happen is this piston could move up and down. If it moved a little, it would stop moving because the O-ring would cover the ports, but then if it had to hit the other way, it could move a little bit either way. So this is a high frequency piston, and they've got them on TTXs, not a piston that has shims. They have a shim piston for TTX 36 and 40 because the piston is solid, it's just a pump. But they have pistons on it when it's a blow-off piston, which means that if the velocity gets real high, it'll dump oil and it won't go through the valves. And they have a high frequency piston, no shims on it, but the little holes and the O-ring and everything, probably for Indian stuff when you're going 230 miles an hour, and you're going even little bumps, they're probably oscillating at a really high frequency. So that's what this is, high frequency piston. Okay, and this is a piston off a NIX 30 Ohlins fork, where they have compression on one side, rebound on the other. This is a compression piston. The shims, this isn't the right shim, it's too big, but I had it sitting here. So in compression, these ports are covered and have shims over it. But in rebound, see how big these ports are, and this is counterboard, and there's a little spring, and there's a shim just like that with a little spring behind it so it can move away when it's going into rebound, and allowing the rebound side to do all the damping and not getting in the way of that. Okay, now we're going to talk about valves, and I'll just start out with this valve. This is this particular shock is a WCJ. It was the NASCAR shock. I think NASCAR still uses them. I know they used them in 2002 when Tony Stewart won the championship on Ohlins on these WCJs, stands for Winston Cup, whatever. And they only allowed them to have one adjustment, so they had a piston bleed on the other side. But they wanted to meter they wanted to do more, and they wanted to do more in compression and meter things. And as we saw, this is kind of the same as that ILX, TTX 36 ILX. There's a separator piston that goes in here, and on the top is nitrogen, but the oil goes in the bottom. And what they did was, there's different bleeds you could get for this, and shims, and I don't remember which way it goes in, but basically it goes in there, and then the tube goes on, and that way when the shaft is displacing that displaced oil, they can meter it and do things just like you do with a remote reservoir, which they weren't allowed to have. But it's really difficult to take the shock apart and do that. So they would buy literally pallets full of these shocks, and they'd valve them differently. And like they were at Talladega, the one that they worked last time they were there, they'd have them hanging up, and they'd have some new ones. And you know, it's a lot of work. Racing is a lot of work, especially on that level. So anyway, this is another type of a valve. Okay, these are the Ttx valves, some of them. And these are the valve holders, or I don't know what you want to call them. This is where you do your adjustments. This is a two-way. This is the one-way, which I kind of prefer. And these are the different valves. This is the standard linear valve, which I really like. This, as we know now, is a digressive valve, which I take off. I find no use for them. There might be down the road, I don't know. And then this is the fancy one that comes on some of them. And if you look on the back of this, that ring, that's the check valve that allows oil to flow back the other way. Like if you're in compression, and this is the rebound side, it has to flow the other way. And on this, those ports for the check seem a little small. There's more ports here. And there's a few other differences. I never could get this to do exactly what I wanted it to do, which doesn't mean much. It's just what I wanted it to do, but maybe somebody else can use it. And what happens is you put the shims on here. This is a bleed around the piston that's metered by the needle valve to see how much bypass there is. This one has the same thing, but it also has another mechanism which isn't there's a lot of little things that are missing here. But basically it does the bleed, but it also has a way to preload the shim stack for high speed. Anyway, that's it. And then this is how it goes. You put shims on here, and then this goes on here, and then there's a spring that pushes this up against the shims that's in the valve body, which you can maybe see in my revalving the ILX video. So there you go. That's about all I know. Okay, so that's it. I hope it wasn't too boring. I try to make them short, but there's a lot of info, and that was only a fraction of the info, but it's a good primer on the fact that there are differences. So remember, authorized Ohlins service and sales, quick turnaround on the service, compete with any legitimate price on sales, and subscribe and hit the little bell, I guess. And next time I'm going to work on a video on shims. Might take me a while, but I'm on it. All right, thanks again. Bye.